Today we are going to do section 6.2 on page 663. Now before that, let's do a quick review of what vectors do. Now that is first, a vector does a vector function, valued function is some kind of RT, where R is the vector function, and is controlled by a parameter t, such that f of t, RT is f of ti, g ti, j, and h of t k if it's in the third dimension. Now what happens is if you plug in the value t, then R will show you the result of some curve on the plane or space that goes around depending on what f, g, and h does, right? And so that those are the endpoints of R. As you plug it in, that's what you get. Next, we have then our R of t can also be written as x of t, y of t, where x of t is f of t. Okay, there is we often use two different names to mean the same thing. That is, x of t is just the f of t is the x coordinate of the vector function r of t, and y of t is y coordinate, etc. And then r prime of t, to take the derivative of a vector, you simply take the derivative of component functions, which is equal to f prime of t, etc. Or you can write it as x prime of t, same thing. And also, it's also, oh, I have a dt there for some reason. Ignore the dt, oops, sorry. Come on, get back, there. Now ignore the dt in here. I just want to say that r prime of t, forget the dt. R prime of t is also written as dx dt. That is, x prime of t is the same as dx dt, and for r prime of t is also dy dt and dz dt. So the next thing, the unit tangent vector is defined as r prime of t, that is the derivative divided by its magnitude. That is, the derivative just happened to be the tangent. The next thing I need to remind you of is the arc length function. The arc length function is defined as the integral of the tangent of r prime, I mean. Yeah, see, because r prime of t is defined this way. So s of t, that is the arc length function, which goes along the length, how long this curve is, okay? So it goes right along here, depending however long, and that is given by this integral right here. It is the r prime of t, u is just a dummy variable. The point is you take the magnitude of r prime is defined right up here on top, and then you integrate it, and that's s of t. Next, let's look at the fundamental theorem of the mean value theorem for integrals, back from calculus 1. Okay, that what it says is that for integration for a reasonable function as f, then there exists a point, I touched it again. There exists a point C such that this C, f of c times b minus a, that's the interval, is equal to the integral, okay? That's a mean value theorem that it has something to do with the average. But just memorize this part, this equation for this section. The integral of f from a to b is equal to some c inside a of b, that f of c is going to be equal to times b minus a is going to be equal to the integral. And lastly, for this section, remember what work is. Work is defined about 500 pages ago as the force dot distance, okay? That is, work is defined as force dot pq. If you're dragging something from point P to point Q, then the dot product is called the work. All right, so having said that, we can get going with our section. Now what we're going to talk about here is called the line integrals. The line integral is very similar to our regular integral, except that we're doing it with a curvy line. For example, normally when we do an integral, we calculate the area under the curve from a to b. Now if we imagine this a to b is some kind of a straight line, we can do this in space where the line might not be straight, but integrating in a similar way. What we're going to do is we have some kind of a function, okay, and we're going to integrate it the same way as here. That is, this curve is r of t, all right, as given that. And we will call the endpoints, give the endpoints a different name, pi. That is, we're going to divide this curve into n sections, as we always do when we do integration. And then the curve is being parameterized. So then there's a bunch of t's, where each ti goes from 1 to n or something, is divided enough sections such that r of t, the r of ti is equal to pi. So you have a bunch of p's up here, depending on the on how your t is divided, and then such that in each section there is a, you can pick a point inside, that's ti star. Okay, you pick where, so which results you a pi star right in here. Okay, so that's inside, and then when you take the value of f at this value times the delta of distance, that's the same as our little Riemann sum, where you find f of value in here, and then multiplied by the delta, what is this called, delta x. Okay, so now being that this AB is now somewhere else, then you take f multiplied by the delta s, and gives you the same f of value of f of pi at this point times delta s, and then you sum it all up, and that gives you the line integral. So basically the line integral is exactly this thing right here, except that you're doing it in space. Now let's look at the page, the next page, 664. As you can see, the definition of the line integral. Now we are only talking about the 2D situation right here. See the 2D? So that is exactly the same as you remember the regular integral is. It's the function, the value of the function at the point times the delta of the distance, right? And then you add it all up and let n go to infinity. And that's the integral of your, that's your line integral. So basically what line integral is that normally your function looks like this, right? Is on the plane, and here's the area under the curve. The line integral is you're doing the same thing, except that bottom line, instead of going from A to B, now is some weird curve. Okay, now it's doing, I don't know, like this, right? But otherwise, the story is exactly the same. You know, your line is twisted, and your curve follows right along with it on top. And so you are integrating, that is, you're integrating like this, instead of, normally we were integrating, you know, like this, based on this line. Well, anyway, so you see that I cut out this piece of paper as a very nice demonstration. Yeah, it's kind of jagged, I don't know why. But anyway, so, but you can pretend this is, well, somewhat smooth. It's smooth enough. It just needs to be continuous for the integration to work. But anyway, so that's the idea, is that you have the ground, the stuff on the ground is now no longer a nice straight line, is maybe curving around. So you have to make allowances for it, but otherwise it's the same thing. And now that is for the 2D, where this line is in 2D. In 3D, is the idea is the same. You just take the function f. Let's see, where's the book? Okay, you take the function f, and then you multiply it by a small section. See, they are identical whether it's 2D or 3D. You take the function f, you multiply by f at each point of your little interval of your curve. Where in 3D, you multiply it by the delta of the distance, of the tiny little distance, and then you add it all up. Okay, and that is the integral in 3D. Now the integral in 3D, it will have to be represented in the fourth dimension, which we can't, but we can do it, whether we can visualize it or not. We can visualize the situation in 3D, which is just, which is just that. So let's look at the next page. We are looking at page 665, where you show how this works. On page 665, we have the curve, right? Where you go down so your line of integration is not straight anymore at the bottom, so it's curved. And that thing, the blue thing, is just like the paper I showed you, right? It goes around, and then the function is the orange thing on top. But you so you have the whole thing is somewhat different, but you just imagine if you straighten it out, it's just like any other integral. Now, I also drew some pictures here to show you how this works. Now, this is something I drew that's similar to what the book showed just now. I have two functions, okay, they intersect, right? And then the function on top is actually, as you can see, maybe a little better, okay, is actually the intersection and that you're drawing on there, and then it has a shadow on the bottom. So that is the function that you're trying to integrate, and the bottom is basically the ground, right? And then what you're trying to do during the line integral is you're calculating the area of the blue section. See, the entire area. So you notice the blue section comes straight down, as if the sun's shining straight at noon, straight down from the top, and the blue section is always straight, okay? There is no curving there. So the area of that thing is what the line integral is for 2 dimensions. And the curve on top is like your new function. So you're integrating, calculating the area where the bottom is in the plane, but the top is curving in space. But somehow the area, however, is still just something that's curved around. Now, I drew this thing. Anyway, so I drew this thing. I would like you to notice that the last curve is not easy to do for this particular function. So please try to draw this yourself just for the fun of it. I guess it's not absolutely necessary to learn the contents of this class, but to draw it yourself is great fun. Now here is how I drew this thing. Okay, the hardest part is drawing the intersection curve, the curve on top. The curve on the bottom is straightforward. It's just something in the plane. Here are some equations I made up on, let's see, which side are we talking about? Let's see, where's my hand? Okay, this side, right. Now this side is what I'm talking about. You see, if you type all that stuff in, then you can create this curve that's similar to the illustration in the book. Now the space curve is very, you can parameterize it, but it's tough to do and a lot of work. So what I did is I did a cheat right here, okay? So I parameterized, this is the curve on the orange surface, the space curve. And instead of parameterizing, I just used the cheat. Now, please type it in yourself so that you will see how I managed to do the cheat. Type that big long thing in, then you'll, and it's long, but it's very easy to do. And a lot of it you can just copy and paste. Once you type it in once, copy and paste it for the second one. But anyway, so that's how I did that. To draw the curve that's in space, remember what you need to do is use the bottom curve and set it equal to the top, the top surface. That is, the bottom curve is the same as an equation equal to 0, z equal to 0, whereas the top surface is equal to z. And when you set them together, then they will be then you can come up with a curve. But that's too hard in this example, so I just did my cheat. Now please do this yourself and see how I managed to do the cute little cheat, which is not absolutely necessary, but it's fun to do. So that's that. So as I mentioned, the line integral, therefore, is just the stuff that we normally do, except the ground is now doing a lot of winding around, so you have to give allowance for it. Now, so please do example 6.14 as part of your homework. This one you're actually calculating from the limit definition, which is fine. It's still very short though. So do that. Example 6.14. Next, let's go to page 666, where we have a condition where we're considering the delta S. Okay, now delta S is, what is delta S? Now, as we saw in a few moments earlier, the length of S is the arc length, that is, the arc length formula gives that delta S is equal to the integral of R prime, right? The derivative of the vector R. Now, if that is the case, then what we have is that it equal by the mean value theorem of integrals. This integral is equal to some ti star, which is something between ti and ti minus 1. That is going to be equal to the mean value theorem of calculus. Of integrals, the mean value theorem of integrals. Let me show you that again. Here, this equation right down here, right, where there exists a number c in the range AB such that this equation holds perfectly. Now, therefore, when your book says that it approximately the same, we actually don't have to approximate. It's exactly the same. So knowing that so this equation is actually exactly the same as long as you pick the right ti prime, okay? And in between that make this equation come true. Now, even though there's a vector in here, you notice that this integral has nothing to do with vectors because you are integrating the magnitude of that vector, which means it's just any old regular integral, okay? Which is why the calculus 1 mean value theorem for integral works. So that equation says exactly, which means that we can substitute it in here, the equation, and then so after we substitute, that's delta S, okay? Now, so we substitute delta S in here, and we come up with that equation, and then when we sum it all up and turn it into an integral, this is what we get, how to evaluate a scalar line integral. The scalar line integral, when you integrate over some curve C, is if you parameterize the curve, right, and then you will be equal to that equation right there. And you just integrate from A to B based on the parameter, and then plug RT in there into F, and then take R prime, calculate R prime, and get the magnitude dt, and that is how you do this. Now that sounds, does that sound easy? Not necessarily, but in this section we keep these problems pretty simple for the most part. So what was R prime of t, the magnitude of R prime of t again? Of course, that's the Pythagoras theorem, which is all the squares added together and take the square root. If it's 2D, then you only have two things, x and y. If it's 3D, you have x, y, and z, but the idea is the same. You just take the square root of this thing, as is summarized here. See, this is how you do the three-dimensional version, and down here is the two-dimensional version. Either way, you're going to do it, right? So as an example of how to plug that stuff in, you can look, please do example 6.15 and then 6.16 as part of your homework. While line integrals might be a bit hard to think about because it's in space, in reality, to calculate it, you just follow the set formula, and then as long as your integration is doing okay, everything just pops out. Now, next, let's look at example 6.17, which arc length is calculated by, as the length here, arc length is calculated by setting the function f equal to 1. And then that will give you the length of the thing. So please do example 6.17 as part of your homework. Next, let's go to page 670, where we consider curves. What's a curve? Now, a curve goes from one place to the other, but which way is it going? The direction the curve goes is called the orientation of the curve. And normally it has two possible orientations. You either go this way or backwards, right? And the same with a curve that's closed just means that it went back to where it started. That's all. And if that's the case, then that is called a closed curve. So that's a curve. The other thing is a closed curve. But yeah, you can see why I might say it's closed. So let's look at the next page, where we consider the work done. Now remember I mentioned that a little while ago that work is defined by force dot the vector of the distance traveled, right? Is force dot pq. If you're yanking that object from P to Q, but that is a straight line. What happens if your object is going around something? and your force is dragging it along. What you do is that you take the tangent of the, what you do is then you take your force right here, okay, and then you dot the tangent of that thing, your curve, that is, there's at some point, and then you multiply the distance a small amount of the delta s. That's the how far you went. So that would be the total amount of tiny little bit of force. Because if you're calculating a small amount in a smooth curve, then each smooth curve is like a tiny little straight distance. So you can take the dot product and then come up with just that little bit, and then you add it all up by integration, and that gives you the full picture. So so as you remember that the details here is that there's the tangent, and that is that a unit tangent? Yep, it's the unit tangent, which means the unit tangent has a vector of 1. The unit tangent times the little distance, and makes it become that tiny little vector, okay, that is pointing in the tangent direction where your force is going. So that's how you approximate the work around some curve that isn't straight. So as a result, the formula of the curve is the formula of the work is called the vector line integral of a vector field force F along some direction of some curve, okay, and that is defined as the force dot the tangent, and then times, and then you let the limit goes to infinity as you, and the force dot the tangent unit tangent times the little bit of arc length that you traveled. Well, that is fine, but how would you do that math in reality? In reality is what we're gonna do is remember what all these things means. That the tangent is given, as I mentioned a little while ago, is r prime divided by the magnitude of r. All right. So then if you plug stuff in, then ds is also equal to the magnitude of r prime times dt. Okay. So then that comes from the arc length equation. Remember when I showed you that S is this equation? So then ds is ds by dt is r prime of t. So that's how this equation comes about. That is, ds is equal to the magnitude of r prime dt. See, that's over there. And so when you plug that stuff in, you get this equation, which the magnitude is happens to cancel out nicely. So you end up with this particular solution right here. That is, to calculate the work done, you will plug in this equation right here. Okay, so which makes the whole thing much easier. Where remember, r of t is x, t, y, t, and z, t from your from the parameters, and dr is taking the derivative. So to calculate this, what is this called? Whatever it's called, the vector line integral. Okay, to calculate this thing, what you're gonna do is remember to take the derivative of the r of t. That's the curve, and then plug everything in, and everything will work out nicely. So to see how that works, please do example 6.18 and 6.19, both of which, as you notice, are very short because they are quite easy to do. So please do example 6.18 and 19 as part of your homework. And then we get to page 674, where we have something that writing stuff in a different notation. At this point, I feel that the book is a bit jumbled in what it's trying to say, so I changed it slightly, so that I edited it to a way so that I think is a bit clearer. What happened is that is the notation. Sometimes the integral of FDR. Did I even mention that? Give me a second. Oh, I realized that I forgot to mention a little while ago that when you're doing this integration, the FTDS, the integral of FTDS, is sometimes also called the integral of FDR, not referring to the president, right? And anyway, so the integral of FDR is sometimes a good way to memorize it. And that is where R is this thing as indicated. Now to do that, dr is the derivative, and then you just plug it in and everything works out. So that's example 18 and 19. So now we are ready to go to page 674, where I have a slight problem with the way the book represented stuff there. It seems a bit, is this 600? Yeah, it is. So I rewrote page 674, just the middle part, in a way that I think makes it clearer. You might not think so, whichever way that you think makes sense to you, right? So here's what I rewrote it. I rewrote it slightly. I just basically, move the stuff around a little bit. Anyway, so here is what happens is that the integral of FDR is sometimes written as integral of PDX plus QDY plus RDZ. So you need to, these two, the reason for that is, well, first let's mention that PQR are the functions of F. And then dr is represented as dx, dy, dz, the vector. And now to explain why that is the case, what we do is that dr is defined as TDS a little while ago, which is also dr prime dt, right? Which is the dx by dt, dy by dt, dz by dt, times dt, which is the same as dx, dy, dz, if you do the cancellation of the dt's. So therefore, FDR is the same as PQR, where PQ and R are the representation of the components of F, X, Y, and Z components. So then F dot dr, that's a dot product here. So you do the dot product, and that's exactly what it says. See, the PDX, QDY, and RDZ. That's why we write it that way, so that it makes some sense. And so when you write down the integral, then that's where we got this, okay? And specifically, from this representation, you notice that the actual calculation is done by this equation, okay? Where that is the dot product means you're going to take the derivative of R prime written on this side, okay? You take the derivative of R prime and you plug it in here and plug R into P, Q, and R equations, and then you integrate, and everything will come out nicely. That whether that sounds easy or not is it is easy. And as an example, look at example 6.20. And so the example of 6.0, if you flip the page, look at the answer. This is it, 3 lines. That's what I mean by it's easy, right? I mean, at least it's straightforward. It's short. Anyway, whether it's easy or not, it doesn't take very much to do this. So please do the example, example 6.20 as part of your homework. It's just one reminder for example 6.20. The formula says take the derivative of RT, right? Here's the formula. So don't forget to take the derivative. Otherwise, you can't get the right answer and can't figure out why. Okay, it's the derivative of RT, but the function itself uses just RT. So you plug in RT, and then you plug in the derivative of RT. Next, let's look at page 675, where we have certain basic properties of vector integrals. And as vector line integrals, which are the same as, well, vector or not, they all work like this, because the integrals basically are friendly to addition, okay, scalar multiplication. And the third one's different, because that's talking about if you integrate this way, you get a value. If you integrate backwards, you get a negative value, which is true in 1D, and true in our original integration, and true in the vector, the line integral as well. Integrating the opposite direction will give you the negative result. And then the last property just means if you're integrating over a bunch of stuff, okay, various sections, you integrate each part and add it all up, as you might imagine that to be true. So to see how that might work, please do example 6.21 as part of your homework, where you integrate over 4 paths instead of 1. So it's like having to do four problems for the price of 1. Next, let's look at the application of line integrals. We are supposed to, well, you just, when it comes to application, when it comes to this, there's not much to talk about. You just do as you're told. Okay, you have the line, and you're supposed to stick a function in there. In this case, the density doesn't matter. And so you stick a function in there, and you calculate the line integral like you are supposed to. In this case, we're back to doing the the scalar line integral, not the vector one. So you follow the scalar formula, which states whatever it states, and you plug it in, and out it comes. So that is, what is this? This is example 6.22. Please do that as part of your homework. And next page, example 6.23. Same thing. It's, what is that? Calculating work. So we're going back to doing work, which is fine. And you do the dot product, the integral FDR, follow the formula, and out pops your answer. Next, let's go to page 681, where we're going to look at the flux. Now, the flux is similar to work in the sense that work is defined as force dot tangent, right? And whereas flux is defined as force dot normal. Normal means the unit normal vector. And there's, well, anyway, so right now, I believe we're only talking about 2D. Yeah, so we are considering the normal vector, and so that you do the dot product, but otherwise the calculation is exactly the same. It's just that you're now dotting, instead of tangent, you're dotting the normal. Now, I should mention that the unit normal vector is calculated, pay attention to down here, which shows you how this stuff is done. Now, like right here, RT is XT, YT, because right now for the flux, we're only focusing on 2D. And so then NT is you just switch that around, slap a negative sign on somewhere. Okay, so if RT is XT, YT, the normal is simply Y prime T minus X prime T. Don't forget to take the derivative, of course. And then the unit normal is that's just some normal, okay? And then the unit normal is take that normal and then divide by its magnitude. And that gives you the unit normal, and then you can fit it into your formula, which is for flux. Flux is the force dot n, with the force being your function, and which is the same as the work formula, except that now we have the dot n, so then you end up something like this. So the flux is defined as, well, anyway, so the flux is defined as F dot n of t, that's some random normal that you calculate from R of t, and then divide by its magnitude, ds, and that will give you the flux. Now, to actually calculate it, however, we have, now let's go to page 682, where we'll figure out how to calculate the flux. Now, the flux being sum of F dot n ds, then it end up being, you plug it in and then dot the normal, the regular normal. And the reason that came out is because if you look at the proof, the regular normal, which is given as this, okay? Now remember that. This is how you're going to calculate the normal, this direct equation, which if you calculate its magnitude, it happens to be the same as R prime of t, because in this case, we're only talking about 2D situations. And so then as a result, then when you write this out, ds is R prime t dt, and then you notice nt at the bottom, the magnitude, and R prime of t at the top, being that they're the same, so right here, you can cancel out. So you only got this left. So it's a quick, simple proof for a formula that's fairly easy to do. as you will see when you do example 6.24 as part of your homework. And as you can see, 6.24 consists of 3 lines total, okay? Or 2 lines if you don't count the, or 1 line if you don't count the first line, which is just the problem. So, so do that. That's example 6.24. And also, let's see, what's this? Next, we're going to talk about circulation. All right. Now, circulation just means that you integrate it on a closed curve. That's what's so circulate about it. And otherwise, there's no difference, okay? So please do example 6.25 as part of your homework. One thing I should mention that sometimes circulation line integrals, people like to put a circle on the integration symbol, okay, to mean, see the circle there? And when you see a circle, that just means the curve is closed. It has no other meaning, okay? So that begs the question that why are we doing that, right? I mean, why draw a circle on a stupid thing? And we don't care if the curve is closed. We just integrate it from when t equals to a to t equals to b. And also, what happens if your curve looks like this? It's sort of closed, but it really isn't. And then what are you supposed to do? So when in doubt, don't put a circle on it. And besides, drawing the circle is a lot of work, right? I mean, the integration symbol is hard enough. You know, you have to do this. Now you have to draw a circle on it. So you don't have to draw the circle if you don't want to. But I just want to mention it in case you see somebody draw a circle on the integral sign and you're wondering, wow, is that something amazing that they're doing? No, no, it's not. They're just integrating around the closed curve. That's all it means. So please do example 6.25 as part of your homework. And what's that? 6.626. Again, you're working around a circle. And please do that as part of your homework as well. And that marks the end of our section. Now, the book wants to mention that when you go stuff clear around, sometimes on special conditions, such as if something, well, anyway, the point is sometimes when you go around, the work might end up being 0. Because you basically did nothing. You got back to where you started. But we'll talk about that more in the next section right now. Just do the homework and calculate the work and stuff, and then you're good. Now, so for homework, please do problem on page 686. Please do problem 45, 47, 57, 45, 47, 51, 55, 57, 63, 67, 71, 77, 81, 85, 87, 89, and 95. And then I will talk about some of the problems when you come back. Now, when you're back, let's talk about some of the problems. Although there really isn't much worth talking about, the problems are mostly quite straightforward. Like, for example, you just you follow the formula, all of them. You know, make sure you follow the right formula, and then plug stuff in, and stuff pops out. That's all I can say about it. Here is 47, and then what's the next one? 57. Where'd it go? I sort of wrote it all over the place. Okay, here's 57. Here's problem 57. Not much worth mentioning. It ended up being -1. And I think the reason I knew that is because I used the calculator over here. So I have the, use the definite integral calculator if you need to. And don't want to bother doing all this grunt work. Let's not do too much grunt work and wear ourselves out. So, and next, problem 87, which is over here. I can't find it. What did I do with 87? On the last page, right. Here's problem 87 and 89, which, again, not much worth mentioning. I just plugged stuff in. If you plug stuff in, follow the formula, and stuff comes out. And in these two cases, I didn't even need to use a calculator. Okay, the integration is quite straightforward. Okay, that's 89. And finally, problem 95 is only slightly worth mentioning. Again, we're doing some kind of line integral, so you plug it in. And, well, you do have to parameterize the line. And this is parameterize the line, which can be done is you usually let I wrote down in the notes that how to parameterize a curve, and please refer to that. That is to parameterize any curve random. I showed you which page in the book. That's example 1.3 on page 16 of your book if you want to do it. Basically, you let x be t most of the time if it's convenient. However, if it's not, then specifically how to parameterize a line that goes from point A to point B, you can look at page 187. To parameterize a circle, of course, we always, or almost always do x equal to cosine t, y equal to sine t. And to parameterize an ellipse, we do x equal to a cosine t, y equal to b cosine t. After you reduce the ellipse into this form, okay, where the number down here is a squared, and the number under y is b squared. And that is going to be 1. That is that's the ellipse that's given to us. It used to be called something x squared plus, x squared plus 4y squared equal to 4. That's the original equation. You divide by 4 so that you turn it into this thing. That way a is called, see, here's the standard form for the ellipse, where a is called 2 and b is called 1. And so then I parameterize the ellipse as x equal to 2 cosine t, y equal to sine t, and t goes only from 0 to pi because that's what the problem wants. And let's see, yeah. So then the bottom straight line where you travel from here back to here, I guess, right? And that is just the line, we'll call it t minus 2 comma 0. And you can just basically make it up, okay? Come up with something that describes the x-axis from minus 2 to 2. So I figured that t minus 2 will work. And then, so once I got all this stuff out, then the next thing is to write down the formula of integral of FDR. Now that, if you do it very carefully and not mess up, which I think I messed up at first, so I got into a mess. But eventually I didn't mess up, so then I plugged this thing into the Desmos calculator, and then the calculator couldn't do it. It was too long or something. So then I broke it up into 2 integrals, okay? That is this part plus the second one, okay? And once that's done, the calculator was able to calculate each part nicely. See, I wrote something else here because at first I messed up something in here, and then the whole thing was messed up. So once I found my mistake and fixed it, then the first integral equals to minus 8/3. The second integral equals to positive 8/3. So the whole result is 0. And that's just the first part, the part around the half ellipse. And then the second part coming along the ground is much easier because y is 0. So if you plug it in, everything's 0, so it goes to 0. So then the entire work done, or whatever this is end up being 0. Yeah. So, and that's that. So this is fairly, the homework in here is mostly pretty easy, unless you got a big complicated integration coming up, then that might become a headache. But I think the ones I assigned are mostly fairly straightforward and except for problem 95. That's the only one that just have a stiff integration situation. So it takes, but if you type it in correctly, it does come out nicely.